Hi everybody. This is the video for lesson 1.2, Limits and Continuity. So we are going to piggyback off of our last lesson where we talked about limits and how limits exist if the left-hand limit and the right-hand limit both exist and they are equal to each other. Today we're going to talk about the concept of continuity. Okay? Continuity. In the word continuity, you can see the word continue. So we are going to examine functions to see if the function itself will continue, will be continuous without any interruptions. Okay? So in simplest terms, if your function looks like it was drawn or sketched from one end of the graph to the next without any kind of interruption, at any point do you have to lift your pen or pencil off the paper, the chances are it's continuous. Okay? So what is the relationship between the three? Well, let's see. Between limits, continuity, and discontinuity. Examine graph A. Is it continuous or discontinuous? Well, in this case, this is a function that is indeed continuous. Okay, so if I were to sketch this, at no point am I lifting my pen off the paper. Okay, so we say this is continuous. Now, how do we define it? Well, let's take a look. Determine each of the following for graph A. Limit as x approaches 2 from the left. As x approaches 2 from the left, the limit is 3. As x approaches 2 from the right, the limit is also 3. Okay? And so then, since the left-hand limit and the right-hand limit are the same, then the limit of fx as x approaches 2 is indeed just 3. Now, we're also going to check to see if it exists at the point as well. Okay? So f of 2 is also 3. So then what we can say is that the function is indeed continuous at x equals to 2. Compare the values you found in part B. What do you notice? They're all the same. Does the values you found in part B support your answer in part A? Yes, since the limit as you approach from the left and the limit as you approach from the right both are the same value, which means the limit of x equals as x approaches 2 is indeed 3, and the fact that f of 2 is also equal to 3, we can say it's continuous. By meeting this criteria, what this is saying is this section of the graph at x equals to 2, okay, this part is indeed continuous. Okay, so this highlighted part, at no point did I have to lift my pen off the paper at x equals to 2 in order to complete this section of our function. So let's look at what a discontinuous graph might look like. Yeah. Examine graph B. Is it continuous or discontinuous? Well, let's do the same thing. X approaches 2 from the left is 3. The limit as x approaches 2 from the right is 4. So by that notion in itself, the limit as x approaches 2 does not exist. What's g of 2? Well, g of 2 is 3, okay? So why is it this dot and not this one? Because this one here is called a hole, which means the value doesn't exist at that point. So g of 2 is indeed 3 because this dot here was filled in. What do you notice about the values you found in part B? They're not the same. So we can say all four of these values need to be the same in order for it to be continuous. So in this case, it is discontinuous. Graph C. As x approaches 2 from the left, of hx, 2 from the left, it is 3. So again, this is saying as x approaches 2 from the left. So again, let's go back to that fridge analogy. We're walking towards the fridge. We're headed there, but we don't know if the fridge is actually there. Okay, which is, saying it out loud sounds ridiculous, but I guess it could happen. So as x approaches 2 from the left, the limit is 3. That does not mean f of 2 equals to, or h of 2 equals to 3. Okay. Limit as x approaches 2 from the right. This is a 4. Since these two values are not the same, it does not exist. So what's h of 2? H of 2 is 6. Compare the values, not the same. not the same. Does the value found in part B support your answer in part A? It sure does. It is discontinuous. Okay. Okay, when we talk about continuity, so these are the different scenarios, the different types of discontinuity you might run into. The first one is point discontinuity. So point discontinuity is essentially a hole. Okay. And then here's a jump discontinuity. That's when we approach a point. Okay. And then it jumps. Essentially, look at this gap here. It jumps at x equals to 1. So this is what we call a jump discontinuity. And then lastly, infinite discontinuity. This would be an example of an asymptote. Okay, so from the left-hand side, as limit as x approaches 1 from the left, it's infinity. Limit as x approaches 1 from the right, it's also infinity. So this is what we call an infinite discontinuity. Okay, and then A, this shows that this is continuous for all points of the domain. So it's continuous between x equals to -3 and x equals to 7. Continuity at a point. The function fx is continuous at x equals to a if f of a is defined and if limit as x approaches a of fx is fa. What? If that was a mouthful, this just simply summarized this. Okay? So it's saying that if the limit as x approaches a point from the left, actually let's go back up to the top. If limit as x approaches 2 from the left is a number, limit as x approaches 2 from the right is a number, and they're both the same, and the point at f equals to 2 is the same value as the limit, then we say it is continuous at x equals to, in this case, 2. Okay. So let's take a look at example 2. Examine the graph. State the domain of the function. So the domain is, well, there's no restriction. Domain is x is an element of the real numbers. Okay, so x can be anything you want. Okay, why is that the case? Because I don't see any asymptotes, and although there is a hole here at f equals to 1 or x equals to 1, it is still defined. Okay, you can see here that f of 1 is actually equal to -2. Okay, in fact, it's stated right here as well. Okay. And again, a piecewise function. This is a piecewise function. It just means that different pieces of this function are represented by different functions. So for example, when x is less than 1, it's represented by a parabola. Okay, just cut off at x equals to 1. When x equals to 1, it's just equal to -2, a value. And then when x is bigger than 1, it's a linear function that just heads straight down. Okay, let me just erase that to clean it up a little bit. Okay, evaluate each of the following. Limit as x approaches 1 from the right, approaches 1 from the right, so x is 1 right there, approaching it from the, from the right. From the right, that is my left. From the right, it is 2. Limit as x approaches 1 from the left is, it looks like 0.5. So what's the limit as x approaches 1? It does not exist. And what's f of 1? -2. And we already established that right there. Is the function discontinuous or continuous at x equals to 1? It is indeed discontinuous. Simply because you can say the limit discontinuous because you can either say the limit does not exist, or that not only does the limit not exist, but the limit and f of a or f of 1, they're not the same. Not the same. Okay, evaluate each limit if it exists. So, limit as x approaches -1 of just the value 5, well, it's just going to be 5. How do I know that? Well, first off, there's no x, so there's no value I got to replace. But if I were to think about the graph, 5 just means y equals to 5. So a line at 5 just is a straight horizontal line that goes all the way across. So at x equals 2, -1, -1, right there, as approaches from the left and the right, it's going to be at 5. Next one, limit as x approaches 2. So what we're going to do is test, okay, if the limit exists on either side. But before we do that, let's just see what the value is at x equals to 2. So we know that fx, oh, sorry, we're just evaluating the limit. So limit as x approaches 2 from the left of 3x4 minus 5x is equal to, and then what we can do is sub in a number from to the left of 2, okay? Now many of you are looking at that and going, can't I just plug in 2 and I'll get my answer? Yes, and the reason that would work, so in fact let's do that right now. 2, 4 minus 5, 2. Okay. So using your calculator, the reason that'll give us 38. So chances are the limit of this function is going to be 38. Okay. But the reason we are able to just do that is because for most of us, we know that this function here is just a quartic function. So we know in our head that it's going to be some shape that looks like that. The graph doesn't necessarily look like that, but we know this being a polynomial function, chances are it's going to be A, continuous, and B, I know there's no holes, there's no asymptotes in this function at all, so chances are the limit is going to be whatever the value is at x equals to 2. But just to be safe, that's not always going to be the case. I'm going to test the limit as x approaches 2 from the right and from the left. Okay, just to see if the limit is indeed 38. And I'm telling you now, it's going to be 38. But let's just test it anyway. So 1.99, 1.99, that gives you 30, let's add one more 9. Let's add 3 9s. 37.9. And then approaching 2 from the right. 001. 38.09. So it's clear that from the left and from the right, sorry, from the left and from the right, it is approaching 38. Okay? All right, so now let's look at this one. So let's say I wanted to cheat a little bit, and I go, okay, I'm going to plug in -3 into this. Let's see what happens. Let's do it. Undefined. Why? Because 2 times -3 is -6. -6 plus 1 is -1. Sorry, -6 plus 5 is -1. You can't square root -1. So plugging in wouldn't work here. So let's test the limit. That doesn't mean the limit doesn't exist, okay? In fact, let's cheat further. I guess cheat's not the right word to use here, but let's use our resources a little bit further and sketch this graph, okay? So if I look at this, I can see, let me just close that. This is the graph for square root of 2x plus 5. Okay? Look, I just graphed it on Desmos. And I can see here that that point is a -2.5. We are looking for the limit at x equals to -3, which is just beside it. I don't even see a graph there. So chances are the limit doesn't exist. Okay? But again, we're going to test it out from the left and the right. So limit as x approaches -3 from the left of 2x plus 5 is equal to limit as x approaches -3 from the right is of 2x plus 5 is, okay, both of these values are not going to exist, okay? But let's do it anyway. So -3, so to the left of -3 is And again, if you have a hard time picturing that, draw a number line. Here's negative 3. So to the left of negative 3 would be negative 3.01, undefined, or does not exist. Now to the right of negative 3, so that's negative 2.99, is undefined. Okay, so they're both undefined, so limit, in this case, it does not exist. Okay, last but not least, let's see what happens here. So I can already see by plugging in 2 into the numerator or denominator, I'm going to have 2 minus 2. You cannot divide by 0. Okay? So in this case, by plugging in 2, so in fact, let me plug it in for you to show you. If I have 2 minus 2, undefined because you can't divide by 0. Okay? So it's going to say it does not exist if you try to plug it in. So instead, I'm going to test the limit on both sides. Limit as x approaches 2 of x minus 2. So from the left is going to be, so I'm going to use from the left 1.999, 1.999 gives me, no, let's add another 9. It becomes a very big number, negative 99. Okay. Now limit as x approaches to from the right of fx that gives me 100,000. So this looks like it's becoming very big, 100,005, so infinity, and this looks like it's becoming very small. Yeah, they're obviously not the same, so the limit here does not exist. Okay, and which makes sense because it looks like there's a vertical asymptote. So if I were to sketch this, there's indeed a vertical asymptote at x equals to 2, and the limits you can see are not the same. One's approaching negative infinity, one's approaching infinity. Okay, and last two examples. Okay, so here are some special cases. Evaluate each limit. So I kind of went ahead and factored both of these. Okay, so for this first one, our first instinct is just to plug in 1. Okay, just to kind of see. You know what? I'll leave that there. What the values would be. Just to kind of see where the limit would lie. So if I were to sub in 1, what would happen is, you know what, let me go ahead and just sub it in so I can show you. 1 squared minus 6, oops, minus 6 times 1 plus 5 over 1 squared minus 3 times 1 plus 2. Undefined. Well, why is that? If you were to factor this out, oops. If you were to factor that, you will see that you have x minus 1 and x minus 1 up top. Okay. So again, with simple factoring to get from here to here, if you're not sure how to factor, please review it. I'm not going to go through it in this video. But if you were to factor it, you would get this numerator and this denominator. You'll notice that the x minus 1s will cancel out, okay? Which tells us that there's a hole at x equals to 1. And algebraically, if you were to sub in the 1 there, 1 minus 1 in the denominator would give you a 0, which again is not possible, okay? So, however, this simplifies down now to limit as x approaches 1 of x minus 5 and x minus 2. Okay? So then, subbing in 1, if I sub in 1 into this, I will get 1 minus 5, 1 minus 2, to give me negative 4 over negative 1, which gives me a limit of 4. Okay. Now again, I am going to confirm, okay, just like up here, this value, I know it's 38 if I sub in 2, okay, but I confirmed it, checking the left limit and right limit. Okay, over here, I know it does not exist, but again, I confirmed it from the left limit and right limit. I guess I could have done it for the first one, but this one is just a vertical line. I didn't think there was any point doing it. Over here as well, if I subbed in 2, it does not exist, okay, but I confirmed it with the left and right limits. I'm going to do the same thing down here. So I got a limit of 4. Let's confirm it. So limit as x approaches 1 from the left of x minus 5 over x minus 2. And then limit as x approaches 1 from the right of x minus 5 and x minus 2. Let's see what I get. So 1 from the left, so that's 0.99 minus 5 over 0.99. Let's have 3 nines in there. Gives me 3.997. And then from the right, 1.001 is 4. Okay, you can see the left-handed side is 3.997. From the right-hand side is 4.003. You can safely say the limit is indeed 4. Okay. Over here, let's see what happens. Last example. As x approaches 0, well, you can already see you cannot divide by 0, so we have an issue here. Okay. So what we can do here is we can obviously test the limit from the left and right of 0. But to solve this algebraically, we can do something called the conjugate method, okay? Which essentially means if you end up with a square root anywhere, and by subbing in 0, you don't quite get the limit that you need, what you can do is get rid of that square root by multiplying by the conjugate. And the conjugate is simply just copy the exact same thing that you see, okay? All you do is change this sign. So this goes from negative to positive to divided by. Now what you do to the top, you got to do the same thing to the bottom. So you get 4 plus x plus 2. Now why in the world would I do that? Algebraically, it's a way of manipulating the equation so that it works. And how does this work? Well, if you look carefully, you can now see, now look at these two brackets. Look at this one, this bracket, and this bracket. Okay. Let me just erase that. They're the same thing. The only thing that changes is a sign. Okay. So what does that tell us? Well, if you think back to factoring for a second, it's something called a difference of squares. If I were to factor that, I would get x minus 3, x plus 3, okay? And if I look closely, that's essentially what I'm doing over here. Okay, so I'm forcing it to become a difference of squares, okay? So then that gives me x squared, okay? And then that gives me 9. So in this case, I'm going to get limit as x approaches to 0, and in the numerator I end up with, now if you multiply a square root by a square root, you get whatever's in the square root. Again, as an example, square root of 9 times square root of 9 is going to give you 9. Square root of 16 times square root of 16 will give you 16. Square root of 3, 4, 6 times square root of 3, 4, 6 will give you 3, 4, 6. If you don't believe me for these three, just type them in your calculator and you'll see. So in other words, if I do square root of x plus 1 times square root of x plus 1, it's going to equal to x plus 1. And that's because two square roots essentially just nullify squaring something. So in this example, it's square root of 4 plus x, so square root of 4 plus x times square root of 4 plus x, it's just going to be 4 plus x. So I'm going to get a 4 plus x, okay? And then how did I get the 9 here? Well, 3 times 3, so in this case it's 2 times 2, So minus 4, because it's a difference of squares. Okay, and then in the denominator, I don't change a thing. Just copy it. The denominator, I just have x times whatever's in the bracket, 4 plus x plus 2. Okay, and then let's simplify what I got. The 4's cancel out, giving me x on top, x at the bottom. Well, would you look at that? What do you notice? Can't these two x's cancel out? They sure can. And that was the issue I had in the first place. As x approaches 0, giving me 1 over just 4 plus x plus 2. Now, what happens if I sub in x now? Is that doable? It sure is. If I sub in x equals to 0 now, okay, I will get 1 over 4 plus 0 plus 2. Square root of 4 plus 0 is just 2, so I get a limit of 1 over 4. That will be the answer to this question, but I like to be extra careful and check my work, so I'm going to check the limit as x approaches 0 from the left of, I can just check the original, 4 plus x minus 2 over x. Okay, and then I'm also going to check limit as x approaches 0 from the right. So let's see what happens. So then x approaches 0 from the left would be negative 0.0001. What am I doing? Oh, what am I doing? So numerator, that should say square root of 4 plus negative 0.0001 minus 2 over negative 0.0001, giving me a value of 0.25. Oh, look at that, 0.25, 0.0016, let's say. And then from the right is just going to be the positive to the right of 0.1. I get 0.2499, which is, in both cases, it's the same as 1 over 4, 0.25. Okay. Now, some of you might be thinking, okay, well, why do I need to know how to solve a limit like this when I can just do this every time, subbing in the left and the right? So that's a very good question, because you need to be able to solve limits algebraically, which is what we've done on the left. Okay, what we've done on the right is just a definition of a limit to confirm your answer. Okay, so in other words, it might be helpful for a lot of these limit questions is, let's go back to the easy ones for a second. Something like this, that's real easy. This one you can just sub in 2, and then that's your answer, 38, just by subbing in 2 for x. Okay. For this one, sub in negative 3, you quickly realize it does not exist. And then sub in 2, for this one, you also realize it does not exist, and you can't simplify that. Okay, you can't simplify that. It does not exist. Those would be your answers to the limits. If you have time after, check it. Oops. I don't know what happened there. Check it by checking the left-hand limit and right-hand limit by subbing in numbers on either side. Okay? Down here. So on the left-hand side, this is solving for the limit. Okay? So once you're done that, and let's say you're running out of time on the test, solve that first to get an answer of 4. That's a nice number. Next question, solve it algebraically using the conjugate method. You get an answer of 1 over 4. Then maybe go back and confirm your answer by checking in the limit on the left and right hand sides. Okay, and that's it. Any questions, shoot me an email. We'll talk soon. Bye-bye now.